Welcome to our second webinar series, First Steps, New Replacement Part Castings Made from Old Drawings. This is part 2 of 4 parts. My name is Julia Speaker, and I am the team lead for the American Metalcasting Consortium's Castings Advanced Systems Technology Integration Team, also known as CAST-IT. This webinar is funded by the Defense Logistics Agency and has been developed by CAST-IT to assist DLA suppliers in successfully supplying these complex cold start legacy castings. In part 1, we introduced that our bottom line secret for first article approval success is collaborative and intentional manufacturing engineering of the processes and all of the tooling among 3 to 5 separate business partners. These partners include a metal caster or machine shop who is typically the awardee, as well as potentially a heat treat partner and maybe even a coder. At the center of it all, ideally taking the technical lead, is the mold cavity tooling builder. This mold cavity tooling builder has both the software expertise to create the tooling as well as the GD&T expertise to understand what the drawing intends and convert it into solid models. Additionally, the way the mold cavity is made today can include significant additive or subtractive manufacturing techniques. It is the mold cavity tooling builder who has access to these technologies and can make the mold cavity more likely to be approved dimensionally using these techniques. Since 70% of DLA legacy casting awardees are now machine shops, and the separate businesses who at the time of the award probably don't know each other, first steps in partnering is very important. That is the subject for this part 2. So that you as an attendee can interact with our team's presentation, I will enable a chat box now. You can use this to document any questions, comments, or discussion points as the webinar progresses. At the end of the presentation, I'll come back and with the rest of the CAST-IT team for a Q&A and discussion. Addressing this important facet of cold start legacy casting production success is our CAST-IT partner Keith Sturgill, who is on site at DLA Aviation in Richmond, Virginia. As Keith will explain, he is engaged daily with the government and commercial entities involved in soliciting, awarding, and approving, or not, legacy castings produced by cold start new awardees. His insight can help you. Here's Keith.
Thank you, Julia. My background is in material science and aerospace engineering, and much of my career has been in supporting aircraft overhaul while working for the Navy in Norfolk, Virginia. My CAST-IT role is acquisition technical support of cast aircraft parts. My current focus is facilitating difficult to procure cast aircraft parts. To assist procurement, the government folks that I engage with are DLA procurement specialists, product specialists, and value engineering personnel here at the Defense Supply Center in Richmond, Virginia, as well as supporting personnel at the DoD aircraft logistics centers, including their engineering support activities. On the commercial side, I sometimes engage with primes for out-of-production aircraft, but mostly I engage with bidders and awardees, who typically are small machine shops and foundries. In my role, I see the difficulties of cold start procurements as they affect both government and business. The common denominator in those difficulties lies in the term cold start. I have listed some conditions that complicate a cold startup, and those would include, first, when a prior manufacturer did not bid or they're out of business. Another instance might be when business partners of the prior manufacturer who participated in the finished requirements are not known or are out of business. And probably, most importantly, when the tooling from prior contract awards cannot be located. And I'm talking specifically the mold cavity making tooling and the measurement fixtures and gauges, and also the machining fixtures. Now let's talk about some cold start realities, as I call them. First, as already mentioned, the manufacturing engineering of the mold cavity making process the mold cavity tooling, the finishing and heat treating fixtures, and machining fixtures, well, they're all lost. Additionally, undocumented exceptions such as red line drawings to the prime's approved 2D drawings are lost. Also, there are other undocumented exceptions to the technical data package, such as specification revisions and changes. They're also lost, so be careful with those as well. And I want to emphasize this important point. The risk embedded in the words above is easy to gloss over, especially with the time pressure of a short bidding window. Now let's look at some risk realities related to manufacturing engineering. Here we have a functional curved profile, primarily based on the size and position of the 4 machined and spot-faced holes. So the question is, how does a machinist set upon the cast surfaces to accomplish what's required dimensionally? In this case, notionally datum A is the inside surface of the 4 machined holes, datum B is the spot face of 2 holes on the same side, and datum C is the end of the 2 arms. So here are the challenges. First, how to build mold cavity tooling so that the casting's arms are consistent dimensionally for positioning the machined holes. Next, how to build the machining fixture touching the cast surfaces to not only put the holes in the centers of the cast hole blanks, but also accurately create the curve within its profile tolerance. Here's a Gantt chart showing the steps necessary to produce a typical cast part. Notice in the bottom left of the first column there, you see the engineering and manufacturing steps and a notional time schedule for a prime or OEM. The manufacturing time for these legacy parts, from prototyping tooling and castings through development of the production tooling and first article approval, was many times in years. Now look at the center of the chart and note the cold start new awardee time schedule. Most of the steps are the same as for the OEM, but the time schedule for the cold start new awardee is compressed. Most contracts I personally have seen call for the delivery of the first article in 120 days. But as you can see, the average production lead time to delivery is currently about 800 days, which is an indicator of numerous delinquent contracts. One might ask, well, why is that? What's going wrong? Well, one takeaway here for a cold start new awardee, where tooling and manufacturing engineering have been lost, is that contractually you have months to accomplish these steps where the legacy OEM likely had years. In this next chart, one can see at a glance the significant change in the U.S. manufacturing mix from 1955 to 2020. Here the number of foundries have decreased from about 6,000 to about 1,900, whereas the number of machine shops have stayed pretty constant. Where in 1955 the machine shop to foundry ratio was 3-to-1, now it is about 9-to-1. What would explain this? Well, one thing, offshoring of foundry services is partially what drove this change. Choosing a capable foundry is not easy. Well, now with better understanding, hopefully better understanding of the risks and consequences, to address the problem of how and who to choose, please keep in mind machine shops are now about 70% of the awardees. The bid window is typically about 8 to 10 working days. So here are some harsh realities to digest. Is there sufficient time for an adequately thorough examination of the TDP? No way, really no way. Will potential foundry and tooling builder partners be evaluated and chosen in preparing the bid? Well, it's not likely. Now, seeing the importance of choosing wisely and the difficulty and magnitude of manufacturing engineering partner choices, how does one choose? As illustrated in the legacy casting with the curved machine profile and drilled spot face holes, this part is otherwise as cast net shape. How would an awardee machine shop know which metal casting processes would first comply with the original 2D drawing, and second, have the tolerance capability to achieve so much as cast net shape? And then lastly, have the tolerance capability to set up consistently in the machining fixture. Well, here is my casted colleague, Mike Gwynn, who is our expert on casting design and the manufacturing engineering of metal casting processes and tooling to accomplish that as cast net shape capability. Mike will explain the two most used metal casting processes for cold start legacy manufacturing efforts and their associated as cast tolerance capabilities.
Thank you, Keith. A common question in a design and manufacturing engineering of a new casting is the tolerance capability of the various mold cavity making processes that could be chosen. And an important question specific to this subject of how and with whom to partner in cold start legacy casting launches is the dimensional capability of the two processes that Gary Burrow highlighted in part 1 of this second webinar series. Those are air-set sand molding with the possibility of using additive manufacturing to print some mold cavity elements more accurately with no draft and fewer mold cavity degrees of freedom. Or ceramic shell investment molding, perhaps using additive manufacturing to eliminate the cost and lead time of making aluminum wax dies and perhaps improve the accuracy of more complex investment cast geometries. So, for a cold start new awardee who is a machine shop, initially studying the legacy drawing and its tolerances, it would be helpful to have an initial idea of what features could be net shape in as cast form. That insight would help the machine shop decide who might be a capable metal casting partner. Coming up is a matrix of all metal casting processes and their baseline or quote best unquote tolerance capability in the simplest plus or minus format. Emphasized will be the air-set sand process and the ceramic shell investment process. As a preface, the next 3 slides show the major factors in dimensional capability across all mold cavity making processes. Let's look at those 3 major factors first. Then we'll turn our focus to 2 more slides that detail the specific tolerance capabilities of air-set sand and investment molding, plus the benefits of additive manufacturing applied to these 2 processes.
This matrix embodies a significant amount of dimensional tolerance information for all metal casting molding processes. Let's start with an overview of how the matrix works. The horizontal green arrow here indicates mold processes with increasing tolerancing capability going across from left to right. The blue arrow indicates increasing tolerance capability as castings are on the smaller side as compared to the larger side. So obviously large castings would have coarser tolerance capability than would small castings. The orange arrow pointing down indicates tolerance capability within these boxes that define each of the mold cavity making processes. So this would be green sand, and there are factors here that the orange arrow indicates, as well as this box here that we'll talk about in the next slide. So within each of these boxes, in this case air set, or over here the ceramic shell investment process, the vertical aspect of each box indicates increasing tolerance capability based on other factors besides just the process itself. And we'll talk about that in the next slide. In this slide, The gray box in the center of the vertical orange arrow summarizes two letters, a letter A and a letter B. So let's talk about the letter A. The letter A in its vertical arrow refers to how the process is designed and engineered for dimensional accuracy. Some of this process design and engineering is how the process is mechanized and or automated. So the best example of that is in green sand, which has relatively coarse dimensional capability in the manual ways of making green sand mold. But in the automotive arena with high pressure and impact, highly automated and highly mechanized, you can see that the green sand process without the actual numbers assigned to the boxes is very accurate compared to many of the other processes going across the spectrum of the matrix from left to right. So the way the process is capitalized is what is represented in the A letter for each of these boxes. In the air set process, there is not as much effect of mechanization because the process is relatively similarly accurate whether it be automated or not. But still, there are other ways of improving the air set process tolerance-wise, which is the reason that the air set box has a vertical distance associated with it. So there are choices with respect to letter A and how these processes, particularly air set and investment in the case of the legacy castings that we're talking about, that metal casters have made in how their shop is capitalized and technically driven. So these are important factors in who a machine shop awardee might choose as their metal casting business partner. Now let's take a look at that letter B in the gray box, tooling design and construction factors. Within each rectangle that defines a mold cavity making process, the letter B and its vertical arrow refers to how the tooling for that process is designed and built. Across all the mold cavity making processes, tooling design and construction has the most significant impact on tolerance capability, generally even more than mechanization and automation of the process. And that's what's going on here in the vertical aspect of the air set box. It's not so much the automation of the process, but it's the tooling design and construction that makes a big difference between the coarse side of air set and the fine side of air set tolerance capability. As we have emphasized many times in both Webinar 1 and in this Webinar 2, an excellent mold cavity tooling builder like Gary Burrow is not only an important business partner choice, but also should be encouraged to take the technical lead regarding how all processes to net shape a legacy casting should be engineered and all the solid models that go with that. Next, let's look at the dimensional tolerance data for all the processes, but focusing on air set sand and investment molds. So here it is. The orange numbers at the tops and bottoms of the mold process rectangles, for example these for green sand, are in millimeters. So to get specific for our low volume legacy castings, let's look at the first green rectangle labeled air set. The number 5 at the top and at the coarse end and plus or minus 0.9 millimeters at the fine end is the best that can be done. So look at the note at the top of the matrix in green. That plus or minus 5 at the coarse end and plus or minus 0.9 millimeters at the fine end is the best that can be done. It is the tolerance that can be achieved if there are no degrees of freedom in the mold's assembly. In other words, parting lines for mold assembly, assembly of cores one to another, and assembly of cores in the mold cavity. Well, now let's look at the investment mold capability. Here on the coarse side, we have tolerance capability that is only plus or minus 0.8 millimeters, and on the fine side, it's all the way down to plus or minus 0.1. Well, why such both tight and narrow range? The ceramic shell investment process is the most accurate of all mold cavity making processes, and it has very limited mold cavity degrees of freedom. The most important factor in the 0.8 to 0.1 is the size of the casting. Gary Burrow explained the limited degrees of freedom which investment castings do have when embedded ceramic cores are involved, especially in part 1, so we won't embellish that now. So from a machine shop new awardee's viewpoint, this matrix and these two processes highlighted in green provide a first glimpse of the surfaces on a legacy casting that can become net shape in as-cast form, and then which surfaces need to be upgraded by machining. Now finally, let's look at the benefits of additive manufacturing superimposed on these two mold cavity making processes. Additive manufacturing options. Additive manufacturing technologies apply differently to the air set and ceramic shell investment mold processes. Gary Burrow explained both fully in Part 1. For our purpose here, the point is eliminating draft and/or eliminating and minimizing mold degrees of freedom so that most of the best tolerance capability can be realized. And we're speaking specifically of the air set process and the fact that additive manufacturing technologies through printed mold elements can eliminate draft or limit the degrees of freedom that coarsen dimensional capability. So that's the way that additive manufacturing affects the air set process. Specific to the ceramic shell investment process, it is often not realized that the traditional aluminum tooling to form a wax pattern has a small draft offset if the draw length in the tool is very long. And wax contracts a little bit, like the pattern maker's contraction difficulty that we have with all the metal casting alloys. So in the case of the investment casting process, you have wax contraction to consider, as well as pattern maker's contraction to consider in the alloy itself. So printing a quick cast SLA pattern or a PMMA wax-like pattern eliminates any small draft offset and eliminates the dimensional allowance for wax contraction. In addition to being faster than building traditional aluminum tooling for wax patterns, there's a small dimensional accuracy benefit as well.
Thank you, Mike. Now let's turn our attention to complying with the technical data package. Remember, there are no exceptions to what is required by the TDP. We cover a case study in Part 3 of this webinar series where a purchased hardware piece part where its hole diameter was cause for the first article rejection. That was the only cause for the first article rejection. Surprisingly, the correct hole diameter could be found only by studying the assembly drawing, which included a note to drill the purchased hardware part, that attachment hole, oversize. Moving on to my next point, that is fully understanding what is to be engineered and manufactured. And I want to emphasize this right now. Intentional collaborative manufacturing engineering cannot be successful if what is to be engineered is not fully known and understood. Fair or not, cold start new awardees are responsible for fully understanding and vetting the legacy casting TDPs. As the contract awardee, to vet the TDP, it is best to choose an employee who has these skills in addition to good engineering skills. First, choose someone who enjoys detail, who enjoys searching for documents referenced in the current specification, but sometimes are not included. And perhaps most important, one who enjoys being rigorous and thorough. If that employee doesn't exist, consider the risk too great to be casual about the TDP. In that case, an alternative might be to find an attorney with an engineering practice. Being thorough and curious is their business. In this vein, it is wise to require a report of TDP subtleties and risks. Well, now that the scope of the manufacturing engineering task is known, how does a machine shop find both a capable metal caster that fits the scope and a mold cavity tooling builder that suits your scope and the metal caster's preferences? The following table provides a starting point. In this chart, one can zero in on who can recommend capable metal casters and mold cavity tool builder partners. For example, if I'm going to make a high alloy investment cast part, but investment wax tooling is not locatable, for typical small quantity DLA orders, I would want to select a mold cavity tool builder that will use investment tooling. It was manufactured by that was manufactured by an additive manufacturing method. The Investment Casting Institute will be a good recommender. As a machine shop, choosing the most efficient machine tools and designing fixtures for the most efficient and least setups is your manufacturing engineering expertise. But unless castings like this, in low volume, are part of your regular machining product mix, then collaborating your design of machining fixtures with the mold cavity tooling builder is necessary. It is that partner who builds the third version of the solid model on which your machining fixtures will be based. The only prudent way for a Cold Start Legacy Casting awardee, who is a machine shop, to wisely choose partners is to ask questions up front of the business partner candidates. And here, for example, are some possible questions you might use for metal casters. First, do you collaborate with machine shops in the design of mold cavity tooling and machining fixtures? How do you collaborate? What's the role of the mold cavity tooling builder in the collaboration? How do you assure that the casting's solidification integrity will enable the required mechanical properties? Now I want to give you some possible questions for the mold cavity tooling builder. Do you take a leadership role in the collaboration of tooling with the metal caster and the machine shops? How do you do that? What happens if you don't lead the design of all the tooling? What's your role in the consequences? Do you build 3 iterations of the casting solid model? First, the model for the finished part for the 2D drawings. Second, the casting with pattern maker's contraction added to all the features, as well as draft, parting planes, match planes, riser contacts, gate contacts, chill prints, vents, and machine stock. And the third, for the casting as it will be processed by the metal caster and the machine shop, that is, the pattern maker's contraction removed, but draft, parting planes, match planes, riser contacts, gate contacts, chill prints, vents, and machine stock remaining. Continuing with questions for the mold cavity tool builders, how do you decide what contraction rate to apply to each dimensionally significant or critical feature? For sand molds, where draft or mold assembly degrees of freedom risk dimensional compliance, do you use AM to print mold elements without draft and with fewer degrees of freedom? For investment patterns, do you use SLA methods to print wax-like polymers directly from solid model number 3? For both these type patterns, sand and investment, who prints them, you or an AM service? Where are they printed? Is there a possibility of shipping damage? To summarize, the 800-day average lead time for cast legacy aircraft components is littered with casualties. For example, aircraft waiting for parts, some badly needed. Awardees having lost money on contracts, or lost the contract, or lost the qualifications to bid or win bids again. Summarize now, intentional collaborative manufacturing engineering among the 3 major business partners is difficult, seemingly time-consuming, but it works and saves all the lost time and cost later. One parting shot. Keep in mind these parts are complex, and the FAT first article testing is rigorous. Passing FAT the first time is very difficult. So when preparing a bid, bidders might consider the cost of a second first article test, a second submission, which would include paying the testing costs for the second submission. As an enterprise, right or wrong, we now inspect 1960s, 70s, 80s, and 90s legacy parts using 2021 inspection technology. OEMs and primes have the important added advantage of understanding how the parts function. But don't discount the reality that these are cold starts. It is you that has to comply with all of the requirements. Now here's Julia once again to open the chat box and field whatever questions or comments you may have. Our team is standing by to respond.
All right, so good morning, everyone, and thank you for joining us for part 2 of the First Steps webinar series. So as Keith said, my name is Julia, and I am the Cast It team lead. Just quickly before we begin the Q&A, I'll take a minute and introduce Cast It. So we are a team of application engineers, and we work to solve both technical and procurement problems regarding castings. So if you take a look in the handout section of the GoToWebinar control panel, you'll see a couple of resources, and these just detail a little bit more about who we are, the type of projects we do, and how our team can assist you. All right, so without further ado, let me introduce the rest of the Cast It team. So we have Mike Gwynn, who is our casting design expert, Dick Tiano, who's an expert in all things 3D data, Keith Sturgill, who's a metallurgical engineer and is great at understanding everything that has to do with DLA and government processes. And then we also have Dave Powlite, who's the VP of Technology at Steel Founders and unable to be here today, but an important member of the team, Gary Burrow, who's a 5th generation pattern maker and all-around casting guru. So combined, our team has over 150 years of experience in the metal casting industry. All right, so let's get started on the Q&A. Let me see the questions. So it looks like the first question I think is probably a good one for Mike. So Mike, regarding partnering with separate businesses, what about metal casters who have in-house machining capabilities?
That's a really good question. And first of all, I want to emphasize that the metal casters are now, about 30% of the cold start new awardees. So a small fraction of the metal casters among that 30% would have in-house machining capability. And that's one reason why we didn't emphasize that. However, if they do, then the important advantage that they have is that internal collaboration that they do on the manufacturing engineering is all done in-house. So that's one factor. And there are even some among the metal casters that have in-house 3D printing of the mold elements, another terrific advantage in complying with these difficult TDP requirements. So it's a rare combination, but for a cold start launch, a metal caster like that has some significant engineering advantages and process and tooling capabilities.
All right, thanks, Mike. So it looks like there's one more question, probably again for Mike. So why is the manufacturing engineering of a prior legacy casting awardee lost?
Well, that's also a good question. And the main reason that it's lost is that there is no equivalent of the government technical data package on the commercial side. So all that was done by whoever the original metal casting or machine shop or combination of these partners that we're talking about had no permanent record of what they did, nor is a permanent record like that, if it did exist, would be publicly available. For metal casters especially, that kind of manufacturing engineering technology and expertise is considered to be proprietary. And then lastly, it's many months at least and years typically between procurements. So the trail gets cold. Even if you could talk to a machine shop and a mold cavity tooling builder and metal casting combination about how they did it, the trail has become cold. Some of the employees involved are no longer working there. So those are the reasons why the manufacturing engineering trail has become cold and is lost.
All right, great insight, Mike. All right, so it looks like that is all we had for questions. So I just want to once again thank everyone for participating in our webinar today. So at the end of the webinar, you will see a survey pop up. It's very brief. We really do value your feedback and use it as we create this content. So if you could take a minute to fill that out, we would really appreciate it. In addition to that, if you have any questions about any content covered or any of the resources provided, feel free to reach out to me. But if not, then have a great day.